everyone, and welcome back to season 2 of fAQ. And hello, Adam. It's great to be back with you on this episode.
Thanks, Tai-Danae. Good to be back with you too.
Yeah, so I thought before we jump into the topic of today's episode, it's always helpful to do a little bit of recap of just season 2 in general, and especially what we talked about last time. So if folks remember, it's been a while, but for the past few episodes, you and I have been chatting about quantum computers, not from a more theoretical, looking in the future point of view, but we really just wanted to get our hands, kind of dirty and into the nitty-gritty application engineering side of things. And to do that, we've been walking through a list of 5 sort of checklist or wish list items called DiVincenzo's criteria. So these are 5 things that if you want to build a quantum computer that works well and actually does stuff, then these are sort of the things that you would look out for. In our last episode, we focused on the 4th and 3rd criteria and really on a specific aspect of the 4th. So maybe just by way of recap. DiVincenzo's criterion number 4 refers to what he calls a universal set of quantum gates. So you have some qubits that you want to encode some information in and process them so that you can get something useful in the end. But how do you manipulate them? These are what quantum gates refers to. And as we saw last time, what this actually means in our specific case of a trapped ion quantum computer, this is what we've been looking at, really refers to a sequence of laser pulses. And so the interesting thing is that last time we honed in on one specific example of a quantum gate on 2 qubits, which did something called it entangled them. So if folks have heard of entanglement, last time we really looked into what does that look like from a concrete math perspective, like what are the lasers doing if I have these calcium ions and they have electrons and I'm looking at energy levels, what's going on there. So that's what we did last time. That was the 4th criterion. The 3rd one refers to long coherence time. So this refers to the ability of your qubits to maintain their quantumness or their superposition before they change in a way that's not helpful for you as you do a quantum algorithm. So we kind of touched on that a little bit last time. But today is going to be fun because we're going to move now to the final criterion in DiVincenzo's list, which refers to the ability to measure your qubits, or if I can just kind of say it the way in the original paper from the year 2000, DiVincenzo's criterion number 5 is a qubit-specific measurement capability, i.e., you want to measure your qubits in a way that makes sense for the system that you have at hand. So we're going to spend a while chatting about that. But even before we get to all of the words there, which was kind of a lot, maybe we should just first focus on this concept of measurement in general. So I'm going to pass things off to you now. When you hear the word measurement, what comes to your mind?
Yeah, I mean, in the quantum context, we talk about measurement a lot, and we've talked about that a lot with the gates the last few episodes that we've been chatting on. When I think about measurement, just like in my life, I don't know, I think about if I'm making some brownies or making some recipe for dinner and it says add, a cup of milk or a cup of soy milk or almond milk, whatever you prefer. I take out a measuring cup, take out that half gallon of almond milk and I measure out a cup or however much it says, and then I dump it into the recipe. So that's one way to measure things. What about you? What comes to your mind?
So usually I think of like measuring someone's temperature, if when you're little and you have a fever and your mom is like, oh, let me feel your forehead,
Yeah.
You're like, is it hot to the touch? Is it warm to the touch? So that's another thing of measuring. So I guess in general, measurement is like ascertaining something that you're interested in.
Yeah, kind of like sensing something like we were talking about, sensing the environment around you. And I can like totally relate to one to measure air temperature today. I'm in our East Coast offices of fAQ, and it is hot today. It's like 90 degrees outside. So it's definitely hot. Sorry. Yeah, and I actually have a little thermometer that I can like look out the window and see how hot it is outside. So that's a way to like gather information about your surroundings. When you're making a recipe, you want to make sure that environment of your recipe has all the right components to it, like the milk and the eggs, butter, sugar, all those sorts of things. And with a thermometer, you want to know how hot either your forehead is, how hot your environment of your body is, or maybe how hot the environment that you're sitting in a hot day out on the East Coast.
Yes, yeah. And I'm sorry, Adam, but it's beautiful in Los Angeles today, so I can't no, I'm just kidding. I'm from the East Coast, so I totally understand how miserable that is, and it's October, which is pretty sad. Okay, so this is good. Kind of what comes to mind when we talk about measurement. However, as we will see in a little bit, measuring quantum systems is a little bit different, because you can't just take your thermometer and, put it next to a calcium atom. I mean, that's not going to be very useful. Before we talk about what it actually means to measure something of interest in the quantum world, I kind of want to set us up for something, because I think we have a few more examples in kind of the classical everyday world to talk about. But what folks may not know, or maybe they do know, is that quite often when you read, one thing we like to do on this podcast is kind of demystify ideas that occur in the popular literature. So folks may or may not know that whenever you're reading a scientific article on quantum weirdness or strangeness of the quantum world, often this topic of measurement comes up. And usually you will find sentences that say something like, when you measure a qubit or a quantum system, the act of measurement changes the system, and that's just weird. This is usually how it's portrayed. It's almost like, when a human looks at a calcium ion or does something to measure it, which we'll talk about that in a second, something like immediately happens or immediately changes that thing that you're observing or looking at. And that's often described as weird. One goal, I just want to say this up front and not bury the lead, as you say, sometimes, is that we hope by the end of this episode we can demystify that a little bit and say why we don't think it's weird. And maybe one way to do that is to kind of talk about another example of measuring things in everyday life and how maybe things do or do not change in that scenario. And then maybe we can move on to the quantum example. So I just kind of wanted to set that up so that listeners are aware.
No, I think that's great. Yeah, I mean, I think that you hear a lot that by measuring a quantum system, you're changing it. And I think that it might be interesting to maybe take some of the examples that we even just talked about and think about, does that even happen? Does it happen the same way in our sort of normal everyday experience? When you're measuring that almond milk, are you changing the almond milk? When you're measuring the temperature of the air, are you changing the air? And I think that a lot of folks might say, no, you're not changing that. You're just measuring it. But I think that if it's all sort of a matter of scale. And I think if you really dig down to a tiny scale, even with those sort of normal everyday examples, you could see that it's really difficult to measure a system without changing it. And in my former life, I was a scientist, and we would be measuring liquids and things like that at very precise scales. And it's really, really, really hard to measure out an amount of liquid and not change how much liquid you have just by measuring it. So think about like that brownie or cake example I was talking about before. You have to be really, really careful when you're pouring out that milk to make sure that you don't leave any behind. And even if you try really hard and you're kind of like banging against the side, there's always going to be like a little bit of residue of that milk left behind. So by measuring out that 1 cup, even if you measured it perfectly, you're never going to get the whole cup out of that. And that's okay in the brownie example and in our everyday life, because we can be a little bit sloppy. Like it doesn't really matter if it's 1 cup, 1.0000 or 1.001 or something like that. You're not going to probably ruin your brownies. And even thinking about like the thermometer example, this might actually be a little bit easier to think about. So let's say, I've got my thermometer that I use to measure the outdoor air temperature. Let's say that it's one of those like old school classical thermometers that have like a little bit of like liquid in there and glass. This one's like a dial one, so I'm not going to be able to do what I'm about to describe with this. But let's say we take that thermometer, like the old school thermometer, and we want to measure the temperature of some water, like maybe a very small amount of water in like a tiny little cup that the thermometer like just barely fits into. If we take that thermometer and measure the temperature of the water, we might get some kind of temperature, whatever, maybe it's, 60 degrees or something like that Fahrenheit. What would happen, you think, if we took that thermometer and before we measured it, we stuck it in the freezer for a couple of hours? We're changing the temperature of the thermometer. And then we took that thermometer out of the freezer and we put it into this very small amount of water. The thermometer is going to affect the temperature of the water that you're trying to measure. So that's kind of what's happening on a very, very small scale. The same thing is happening to my thermometer outside, where all these air molecules are sort of bouncing around and some of their energy is going into the thermometer, and we're reducing the energy in the atmosphere of those air molecules by just a super, super tiny amount, nothing that you would ever notice because the scale is so big. But if you bring that scale down to pouring that liquid out of a measuring cup or using a thermometer to measure a very small amount of medium like water, especially if that thermometer is at a very different temperature than what you're trying to measure, then you can kind of see that measuring can actually affect a system even in our everyday lives. It just usually doesn't matter that much. And I think there's a big difference in quantum. So I know we'll get to that, but maybe I think we had talked before a little bit about other things that you can measure that are maybe a little bit less straightforward in everyday life. Should we maybe talk about that a little bit?
Yeah, let's talk about that, because I think that this one kind of gets at the theme for our trapped ion quantum computer in a bit. So please go ahead. Yeah.
One thing that I was thinking about with trapped ions, like we've talked before about, you're using lasers, so you're using light to measure things. And that might seem a little bit strange, but I was thinking about it a little bit more. And I don't think that's actually very strange, because we use light to measure things every day with our eyes. So if we're, measuring the color of a plant outside, or I have a plant behind me over there.
Beautiful.
Thank you. So if you wanted to measure the color of that, you could just look at it. And the way you're measuring the color is that there are photons from the sun, in this case, because I don't have any lights on inside my house, photons coming from the sun, hitting the leaves of that plant, bouncing off and going into my eyes. And I'm then, based on the wavelengths that my retina is detecting, my brain interprets that color as green. So I'm sort of measuring those leaves as green. So you can use light to measure things just in everyday life. And in fact, you do that all the time. You might just not be thinking about that as a measurement. And just like how we talked before about how measuring things can change the thing, I think we've probably all been, driving around in a car or seeing cars driving around and paint on the car is fading, or a sticker, like a bumper sticker or something that was stuck on the back. The colors don't look as bright as they probably used to look. And that's because the light that you're using to detect the color of that object is actually photo bleaching or chemically changing the dyes that are inside that paint or inside that bumper sticker, and bleaching it, making it lighter and lighter in color, and removing some of the sort of vibrance or deepness of that color. So the light that you're using to be able to detect and measure what color it is actually also changing the system by bleaching it out. So that usually doesn't happen on such a quick scale that you would notice it as soon as you put a new bumper sticker on. It just goes very slowly over time. But again, it's that sort of scale issue. In that case, the scale is time instead of like a small film of milk inside your measuring cup. What do you think?
That's brilliant. I mean, we could just end the episode now, because I think you just captured the heart of it. So I like this light example, because in order to measure something like color, or to look at it, what does looking at things entail? It's what you said, light from some light source, whether it's the sun or the light in your ceiling or whatever, comes to an object. It interacts with that object, and then it bounces off and then enters your eyeball. And those photons then transmit signals into your brain, and then this processes as sight. So in order to observe something, you are using the fact that photons have interacted with that something, and then you're like the recipient of that information conveyed by those photons. And that's exactly what's happening when you're measuring your qubits in a trapped ion quantum computer. And as you mentioned, we have hinted at this several times in previous episodes, but let's now just be explicit and just say, what does it mean now, in light of the examples they've given us in everyday life, to measure one of these calcium ions? So maybe now we can recap a little bit. But for a calcium ion, you're interested in its energy level. And we have talked about this, whether your valence electron is in the ground state or whether it's in an excited state. And ground or excited, these are like your 0 and 1, your 2 units of information that you can then use to do computation with. And so let's suppose that we have, our qubits in our trapped ion quantum computer. We've done a whole bunch of operations to them in terms of laser pulses, i.e. quantum gates. And now we want to measure out the result at the end. So what does that look like? Let's just say we have 1 qubit for simplicity, but we remember they're in a chain. Okay, to measure means we as people either want to know, is the qubit in ground or excited? Maybe it's in some superposition, which means if we measure it, there's some probability it'll be in ground and some probability it'll be in excited. But what does it mean to find it in either one or the other? Like, how do we know? We can't ask it, hey, qubit, how's it going today? So, like, which one are you? We have to interact some way. And that's where light comes in. It's exactly what you said with lasers. So I believe this is how it works for the specific case of calcium-40 ions. So you have a qubit, you shine a laser, you have a laser pulse with a specific frequency such that it excites, if your ion is in the ground state, it excites it to a higher state, kind of like an auxiliary state, which is like a temporary short lifetime thing. And then it'll immediately go back down to the ground state. And in relaxing, it gives off a photon or a little bit of light. So then you can use like a photomultiplier, and so you can kind of amplify that a little bit. So if it's in the ground state, you kind of pump it up and then it relaxes down. And by doing that, it gives off light. So if you see your qubit fluoresce, you say, it was in the ground state. And then it turns out if you do this process, but your qubit was actually in the excited state, that laser pulse is kind of invisible to the excited state. So it doesn't do anything and you don't see light fluoresce. So this is how measurement is done in a trapped ion quantum computer. You shine laser onto your ion, you let it interact with the ion, and then it does something, namely what I just said. So either you have 2 options. You see it fluoresce or you don't see it fluoresce, i.e. it's in the ground state or it's not in the excited state. So that's measurement. Now, where's the weird part? Because that doesn't sound weird to me. That sounds very normal. So where's the weird part? So I think I should just say this explicitly, and then we can chat about, is this weird in light of everything, all of the examples that you gave? So maybe this is like the unusual, not intuitive thing, but prior to this measurement, prior to this laser pulse, you say, okay, my ion is in some superposition. Okay, so maybe it's like 70% ground state, 30% excited state, as an example, just making that up. But you actually never know what it's going to be. So you could actually have gotten excited, even though it was less probable, but it could still happen. So the interesting thing, though, is if you measure it and you find it to be an excited, and then you shoot it with the laser pulse again, you do the exact same thing again, it's not going to be either one or the other again. It's actually you're going to get excited. And if you do it again, you're going to get excited. And if you do it again, you're going to get excited. So here's maybe the weird thing, I think, is what people are thinking is kind of strange, is that when you measure it, you sort of destroy the superposition. Before measurement, it was like, either one, there's a little bit of randomness. But as soon as you let this laser pulse interact with your ion, then it kind of, the word is collapses, like the probabilities collapse onto one of the options, and it's forever and ever, I'm in on that option now. So maybe that's the weird thing that people are saying. There was some randomness before measurement, but somehow by you observing it, i.e. by the laser interacting it, the laser sort of removed the randomness, and it fixed the quantum qubits so that now it behaves as like a classical thing. I don't know. Does that seem weird to you? Or
yeah, I mean, I think like I'm hearing you talk about sort of 2 different things. One is measuring with light, and you shoot a photon, and then you get either fluorescence or you don't get fluorescence. That makes a bunch of sense to me, and I think I kind of see a parallel there with the example of like my plant behind us. Mm-hmm. That like the photons coming from the sun, like there's a lot of them, and certain wavelengths that hit the leaf are absorbed, certain ones are reflected, and depending on that mix, that's what the color is. So it's slightly different than I think what you're explaining with trapped ion quantum computing, because it's not really absorbed or reflected. It's either I guess, absorbed, and then there's a fluorescence. So the ion or the electron can absorb the energy and then fluoresce at a different wavelength, which isn't really like a reflection. There's been like sort of a transformation there, or it just passes right through. So there's like some differences, but that makes a bunch of sense to me. But yeah, I'm still kind of stuck on this like superposition collapsing thing, to be honest with you, of like you're giving some energy, you're measuring things by giving that energy in through a photon. And then you could have had a superposition before that if you ran that qubit through the correct gates, which we talked about before. But what is it about that photon or that laser that you're shining in the qubit that's in superposition? What is it about that collapses or freezes or locks down the probabilities from like what you were talking about, 70 and 30 to like 100 and 0 or 0 and 100? Like that part does seem a little strange to me. Like what's going on there?
Yeah. I don't know, Adam.
Okay.
I don't know. So actually this is relevant. So before we jumped on this recording, I was doing a little searching on the interwebs to see what people are saying about this. So I was reading this article on Scientific American, which is talking about these ideas and what's really going on and why is this confusing to people. And so it turns out that the physicist Werner Heisenberg in the 1920s was the one who postulated this interpretation of what we observe in the lab corresponds to like this superposition or this wave function collapsing. You know, like I love our analogy in season 1 of fAQ, where superposition is like a bar chart, where you have bars of different heights sort of enumerating your different things that you can see, where the heights are kind of like probabilities. So it's exactly what you said. We first had 70 and 30, and then it's like it collapsed to 0 and 100. So what is that going on? So the word collapse, or that idea, was introduced by Heisenberg. But the article says the only flaw with this idea is that there is nothing in the equations of quantum theory that says a collapse occurs or offers a physical process to explain it. So when you asked me, like, what's physically going on that it would cause all of a sudden the qubits to say, oh, no, I don't want to be in superposition of 70, 30. I am like forever 0 and 100. Like I am all or nothing. What physically happened? I don't know. So apparently people haven't known since the 1920s. And the article says, this introduced a new theory. What exactly, a new mystery into the physics. What exactly happens when a wave function collapses? That quantum conundrum is now known as the measurement problem. So I think the measurement problem is we observe a phenomenon in the lab, okay? Like our mathematical tools only allow us to go so far. They only allow us to say, with some probability, we will find fluoresce or not fluoresce. Like why? We don't know. What we do know is that when we measure it, it doesn't go back to some probabilities of one or the other. It's like all or nothing at that point. Why? We don't know. So I think that's really interesting.
Yeah.
It shows, there's like definitely limits on human understanding, which I think is fantastic to think about.
Yeah.
But I think, the question you asked is the question that, people have been asking for like 100 years.
Oh, well, I'm glad we're in good company then.
You're in great company.
Yeah, because, I haven't really looked into that before, and I don't know, I definitely don't have like hypothesis or anything like that. But it is, to me, it's like inspiring or motivating that there's some edges left to be explored. So if I can read it back just to see if I'm understanding what you just said. Basically, we observe this phenomenon, or physicists, engineers observe this phenomenon of measurements and going from superposition to collapsing into non-superposition. That's like repeatable. It's like very reliably happens. The math like kind of can describe it, but it doesn't describe why it happens. We just know that it does happen, and we have mathematical equations so that we understand that it happens, and we can prepare for it and use that in engineering and in quantum computing and in quantum algorithms and all of that. But the actual, so like the practicality fine. We've got that figured out. We know what happens practically, but what's happening like functionally under the hood, like there's still some like dark spots in our knowledge there where we don't really understand what's happening under the hood, but we understand what's like functionally happening or practically happening when we run these experiments. Is that right?
Yes, 100%. 100%. So I personally love dark spots. I mean, I love mysteries. I think it's tantalizing. And I mean, it can definitely keep one up at night, I think. There's so many exciting questions. So I think you captured it well.
I think that's cool. And if folks watching this or listening in on our conversation have ideas about this, or just have a more academic knowledge, or just interesting ideas, like let us know in the comments. I would love to hear what people are thinking about what's actually happening in there. That would be really interesting for me.
That would also be a Nobel Prize.
Sure. Yeah, do it. From FAQ. In the comment section of FAQ, yes, you can earn a Nobel Prize. Just comment away.
Okay.
It's possible.
Great. It is absolutely. Okay, so I think that this is this it for measurement? We kind of said what it is in trapped ion systems, and we talked about maybe why, interacting with something and causing it to change is not weird on the surface, but maybe there's some definitely unanswered questions of quantum physics. That can be a little bit weird.
Yeah, no, I think that covers most of it. I can try to talk a little bit about superconducting qubits.
Yes.
That's what I usually try to do here. So I'll give it a shot. This one was a little bit tricky for me. I've been doing some research on it, and I definitely don't fully understand all of the details, but I'm happy to at least let you in on what I found out, if that works for you.
Yes, I would love to hear.
Okay.
Please share.
Okay. So there are some similarities and I think some differences in how to measure the state of a qubit in a trapped ion quantum computer versus a superconducting quantum computer. So some of the similarities are you're using electromagnetic radiation. So in the trapped ion scenario, we're using a laser. In a superconducting quantum computer, we're using microwaves. This is all electromagnetic radiation on the spectrum. We just have visible light is different from microwave light, different from ultraviolet light, infrared light, gamma radiation, X-rays. These are all on the electromagnetic spectrum. So it's just a different sort of frequency. So to do that in a superconducting quantum computer or superconducting qubit, you first put your qubit, or this is one way to do this, put your qubit into what's called an optical cavity, which is basically a metal box. So when you're building your qubits, each of those qubits needs to be in one of these optical cavities. And one interesting part of some of these optical cavities that are used, or some of the more popular ones, is that they have mirrors on the end of the box. This cavity that you're putting things into, it's a closed box, and there are mirrors on the end facing each other to the inside of the box, and the outside end on the other side of those mirrors is transmissive, so you can shoot microwaves through it. So you can get microwaves into the box through the ends, and then there's mirrors there to kind of help amplify and bounce things around for what gets through. But the interesting thing with some of these cavities is they will only let in certain wavelengths of electromagnetic radiation, or certain wavelengths of microwaves in. If they're not the right frequency, they don't get into the box. That's like the simple way that I've been thinking about it. So you can only shine certain frequencies in, which is good because you want your qubit to be nice and isolated. And the idea is that you shine in a certain wavelength that can interact with the qubit in some way, but you need to make sure that wavelength is very different than that energy gap, because these are artificial atoms. So they work very similarly to the atoms that we've been talking about, these ions, where there's electron, and they're artificial, but we're basically modeling those valence electron jumps. And we don't want to give it the right microwave pulse to get it to jump up or jump down. So it has to be a different wavelength that can still get in there. So there's lots of engineering challenges here. But the idea is you shoot the right wavelength in there, and if it interacts with the qubit, it will scatter the radiation. So you can talk about these as photons as well, like a microwave photon. So if a microwave photon gets in and interacts with the qubit, it will interact by taking some of the momentum away from the photon. There'll be like a collision basically between the microwave photon and the artificial atom qubit of like where that electron sort of is it energized or not. Depending on what state it's in, that collision will impart a different amount of momentum and energy to the photon that then scatters. And then that scattered photon can be measured by photomultiplier tubes, like you were talking about before, and you can gain some information on that photon that has scattered after it hit the qubit. So you can think about it, there's been like an information transfer from that artificial atom to the photon. And as that photon scatters, a little bit of information about the position or the state of the qubit was transferred to that photon. And then you can measure that photon and kind of back calculate what was happening with the qubit. So there's a lot more complicated stuff that honestly, I don't understand a lot of it. I'm still learning, but those are like some of the kind of basics about how you can measure a superconducting qubit and a superconducting quantum computer. So I think you'll see there's like some of those similarities where you're still using electromagnetic radiation. You're still like measuring a change that happens when you hit that qubit with some electromagnetic radiation, but then there's a bunch of differences too. I hope does that make sense a little bit?
Yeah. Yes, it does. That was a very clear, high-level explanation. Thank you for doing all of the hard work for us so that you could come and explain it.
Good. I hope I was right.
Nice.
If I wasn't right on any of that, again, the second Nobel Prize, comment below and help me out. Maybe you'll get a Nobel along the way.
Yeah, or at least a thank you from us. Just in case people are like, wait, what did we do in the past episode? Or if this is your past episodes, or if this is even your first time tuning in, I think it would be appropriate for us to conclude just by doing a really quick recap of all of the criteria that we talked about. So just to wrap up with a quick summary, the 5 things that we have been chatting about are as follows. DiVincenzo's first criterion, we spoke about having well-characterized and scalable qubits. So a system with well-characterized and scalable qubits in trapped ion systems. Are ions well-characterized? Do people understand a lot about them? Yes. Yeah. Are these systems scalable? Meh. I mean, if they were, then we would have a real fault-tolerant, powerful quantum computer and everything would be different. Not everything. Lots of things would be different these days. We don't quite have that yet, but it's what folks are working towards. Yeah. So, yeah, they're working on it. Criterion number 2, we talked about qubit initialization. So the ability to put your qubits into some sort of starting state, this fiducial starting state. So something that makes sense that you can kind of go back to restart your calculation. I liked your example at the time, which was if you pull out your calculator, you want to zero it out. Like you just want to make sure it's starting at 0 before you punch in some things and crunch a number. So we chatted about that. Do people have the ability to do this in trapped ion systems? Yes, thanks to optical pumping technology. This is well understood. And then as I mentioned at the opening of this episode, we chatted about criterion number 3, long coherence time. So you'd like to choose a system such that your qubits maintain their quantumness or their superposition states long enough so that you can do your laser pulses. And you also don't want your laser pulses to be so long so that your qubit loses its superposition, in which case your laser pulses are useless at that point. So that the amount of time that your qubits can retain their superposition states is important. So we talked about that. A universal set of quantum gates. This universal meaning if I have any algorithm that I want to implement, can I do that with the equipment in my lab, meaning my lasers or my microwave pulses? And the nice thing is that essentially any sort of quantum gate that you want to apply to multiple qubits can be applied in sequences of 1 and 2 qubit gates, i.e. you kind of operate on your qubits 1 or 2 at a time. So we spoke about an example of a 1 qubit gate a couple of episodes ago. Last time we talked about an example of a 2 qubit gate just to get our feet wet. And then finally, the 5th criterion, what we talked about today, the ability to measure your qubits. And so in the case of trapped ions, that's shooting them with light. Just like when we look at things like the beautiful ivy plant behind you, a little bit similar. So that's a short recap. I hope that was helpful for folks. And yeah, as I said, I thought this was a great introduction, at least, into the exciting world of quantum physics.
Yeah. Thanks, Tai-Danae. And yeah, thanks for the recap. And yeah, this has been a lot of fun. I've learned a lot along the way. Hopefully other folks have too, as they're listening to us. And thank you so much for taking all the time to walk me through the mathematics and to get this kind of not so mathematical person, meaning me, excited about some of these aha moments. I remember looking at the curve of what superposition actually means and some of these other algorithms and formula that you've showed that really have helped me understand things a little bit better.
Okay, Adam, I think that concludes our journey into DiVincenzo's criteria. That has taken us several weeks. I don't even know what we started. What year is this? I don't even know, but we did it. So I just want to say high five to you. I personally learned a lot from this. I think I said even at the beginning, since I have a math background, I know some of the math, but the math is very, it kind of can feel removed and very abstract from the actual engineering and practical side of things. And so I just loved your idea at the beginning to go through this checklist, which sort of made us take our time and go into the details. So I personally thought this was fantastic. Thank you so much for doing this season 2 with me. I had a lot of fun.
Me too. No, this is super fun. And I definitely learned a ton. And hopefully anybody who was listening in on our conversations learned a little bit along the way too. But it's been a really fun, just a fun journey into how these types of quantum computers work. And I've learned a lot about trapped ions, but also just learned a lot about physics, honestly.
Yeah. Well, this was fun. I had a lot of fun. And I know that we have exciting conversations, lots of things that we can chat about in the future. So thank you, Adam. And thanks to everyone for watching on this episode. We appreciate it.
Thanks. Bye.
Bye.